Okay, let me start now. So here, in the previous lecture, we did a simple regression. Let me say, let it be ending here, perhaps. Let me take it up. Take it all the way. So we just took a simple data set of age and heart rate. And now let's say our default testing is for slope equal to 0. Now let's move on to some simple examples of multiple regression. So here the model is again, let me write down the model is linear model is y is equal to beta naught plus beta 1 x1 and so on. Right? So let me write that down. So let me write it in vector form y is equal to x beta plus epsilon. Epsilon's all linear ID with mean 0 and uncorrelated with epsilon rate sigma squared. And we'll assume that we'll put some variance appropriately, and then we'll also assume normality as well. Very good. So let's just do a simple data set. Let's just do simple data set. Let's just start with x equal to 1:10. 1:10, and let's say y is equal to let's sample 10 points from 1:100. So sample 10 points from 1 to 100. That's all right? So it's minus. Very good. And let's do a simple fix. Let's say z is equal to x plus y. Here, there's no error term. So z is x plus y. There's no error term. Z is the I guess my y above is my z, and my x1, x2 are we should call them x1, x2, and y x1, x2 perhaps. And then let's call this as y is equal to, let's say, x1 plus x2. Let's call this again, that way it's clear, same thing. So no error. So my y is just is exactly like x1, x2. So now suppose I do the linear regression, it should give me a perfect answer. Let's see if it does that. LM of y, and I have to do tilde x1 plus x2. That's what I have to do. That's the decimal side. So if I do this, so let me go back here in the code. So LM of y tilde x1 plus x2. So if I do that, what do I get? Let's do that. Then look at this. It's giving me a near perfect score, right? So intercept is this. It's like 0, and then so x1 plus x2. So exactly it gives you that. So beta naught is 0, beta 1 is 1, and beta 2 is 1. So it gives you exactly the answer. So it R does pretty, so no problem. So now let's go and add some error. Let's go and add some error. Let's see. So what did it do? It found out. Let's go. It found out that let's go Let's write down what R found out. The R found out that beta 0 is equal to 0 almost. Beta 1 is equal to 1, and beta 2 is equal to very good. Okay. Now let me go add some error. Let's add some errors. No, notice there's no errors. Notice no error in this case. So variance of error is 0. You can do mean 0 variance. Now let's go to the next one. Let's go and do, let's take the same model. X1, x2 the same. Then let's go and add. We're going to add R norm. So Z is a vector, Y is a vector. Let's say R norm, let's say 10 points, right? 10 points of 10 points of variance 0 and 2. So I've taken ID normal 0 to. So standard deviation is 2. So sigma is 2. So sigma is equal to 2. Let's do that. Let's say that's your Y now. So Y is a little jittered now. It's not the same thing. Let's do the same command. Let's go and then let's see what it finds. Let's see what R finds. So R is now finding here that the intercept is minus 0.9, beta naught is 0.9, and then 1.0. This is what I got. You may have gotten some number. So I'll write down properly what you guys got. So So what I got was when you try to do my regression number, but this is what I got, minus 0.9, 9026. I got this beta 1 is again 0.987, 9837, and then below we got beta 2 was just 1 point something, 0.1. Very good. So this is how R is understanding there. This is quite cool to check. Right? So now let's try and let's try and increase the sigma. Like let's try and put more noise. And so we're jittering the points quite a bit. Let's just try and see. Let's try and do again. Let's take the same thing. Let's just take sigma. Let's say 10. So 10. Let's say sigma to 10. So the variance is 100. So from 4, I'm going to 100. This is a new y. So the new y. So the new y. So we clean these plots out. This is my new y. And so we go back here. I know what's going on here. The new y. Let me do again LMs. We go back here and we plot, we type LMs. Same thing. Let's try and do this. So here I should get again. So the intercept is moved up now. It's like -4, and I get x is 1.28 and y is from this. So again, let's just write it down. So the thing changes. Very good. So beta naught is -4.547. Beta 1 is 1.289. And beta 2 is 0.98. Very good. That's what you're getting. So you can just see as we add more and more noise, your guesses will get worse and worse, right? So again, the difference between the beta i's is controlled by the standard error and standard deviation of estimates, right? That's what beta hats is this one, and it's kind of related to sigma squared and the of the error term, right? So we notice that the estimate gets worse as sigma gets larger. And this we know, right? This is expected from theory. This is expected from theory. Very cool. So the syntax is fairly easy to use. There's really no problem. And then you can also do summary command and check everything if you want. Let's do summary command. Let's do summary of let's see what all it summary of, let's say, LM of y tilde x1 plus x2. So the multiple regression, let's do that. So it gives you all these numbers. So first is it gives you the residuals. The residuals are like the errors, that is the start low as -8 and as high as 15. And that's what it's giving the first term, right? So the first is a 5-number summary of residuals, right? So the first residuals, let's copy down, residuals is the 5-number summary of residuals. Right. So and there also, as we know, the available residuals command as well. You can go back and do it like before. And the other thing is that the regression coefficients are presented in a table, right? So which includes the estimate. That is, the first column is the estimate of the. So intercept is 10. Intercept is whatever we got as -4. The first slope beta naught is beta 1 is beta 1.28, and beta 2 is 0.98. And that's what we got. That's the second column. That's the first column. That's the estimate. The next one is the standard error. That is the error of beta naught hat, beta 1 hat, and beta 2 hat. That's the error. Next one. And the third one is the t value under the hypothesis that beta I is 0 and corresponding p value for a two-sided test after. Okay, very good. So then let's see. So that means let's just write the first column. This is the table, the regression table. Let's call it. table. The first column is the estimate. Second column is the estimate of beta naught, beta 1, beta 2. Right? The second column is the second column. Slowly, first column is this. The second column is the standard error. And the third column is the t statistic for each of them. Right? T statistic for each of them. The column is the t statistic. And the fourth column is the p-value. T statistic for beta equal to 0 for all the beta for each of the para estimates equal to 0. Each of the parameters, each of beta naught, beta 1, R does a default, right? Beta 1, beta 2 equal to 0. And the fourth column is the p-value. We've seen this before. I thought I'll do it again slowly. Just get the answer. And p-value for two-sided test. For the two-sided test. That is a two-sided test means what? That means the first null is that the null hypothesis is that the null is that they're all 0. The alternative is that not 0. I've written it precisely the notes. I've written it. The other tests also you can check. It's not that hard. So this is once you do this, then the standard error residuals also are given in this row. So that's given this at 10.6 and 7 degrees of freedom. So the next after the table, this is a regression table, right? The next is the residual standard error. And corresponding degrees of freedom. Error and corresponding degrees of freedom. It's quite likely done. We took 10 points, and so it's very nice. Then it also gives the R-squared statistic. So R-squared, how do you do it? It's the fractional variance explained on the model, right? That's what gives the R-squared statistic. R-squared statistic, which we discussed in class long time back, and it essentially gives you the fractional variance explained by the model, right? So you think of it like that. Think of it as fractional variance explained by the model. And finally, F statistic. Right? The F statistic. So F statistic is the one in which you test everybody is equal to 0 and equal to the same guy. Right? So all the betas are 0. So F statistic is the one that is null hypothesis is that beta 1. You just say each jointly you test beta 1 is equal to beta 2 is equal to beta 0 is equal to 0. That's a null hypothesis against alternative type testing. So this we have already seen. We'll see today also. It comes from the ANOVA. It comes from the analysis of variance. From analysis of variance model, ANOVA model. Very good. In our case, what the F value? F value also is very, very. The P value is quite small. It's not that large at all. So it's like very small. So that means it's not enough evidence to reject our hypothesis, which is what we also saw. Very good. The data itself is x1, beta 1, beta not 0, but beta 1, beta 2, and are 1 and 1. Very good. Now let's go a simple another similar multiple regression from a real data set. Let's say not from a simulated one. Let's go back to this one. So this we will need to load a package called Lattice. Let's go library Lattice. I don't know if you have it in. So I want to introduce the package lattice, which I will LATTIC. So I think I've already installed it. Hopefully you have installed it. This has been contributed by a colleague in IIT Delhi called Diploma. You can look at that page as well. So once you do that, so I'll into lattice, and then they have lattices have data sets. So let's use a data set called home price. Let's say home price. It's called home price. Yes, home price. Let's do home price. Data home price is not found. Why is it not found? Let's say I have to attach it perhaps. I'm not sure why. Maybe I've using R. Let me use, sorry, 1 second. So you have to install a package called using R, and then that's due to John Verzani. I think John Verzani's book has it. So then once you install using R as well, then you can do a price called data home price. So once you've installed home price, let's attach home price and let's sort of play with it a little bit. So let's create let's do a little bit of graphics using we've done ggplot, but we've not done things with lattice. Let's just do some graphic. Let's attach home price. This thing. Then I want to just create some plots and see what home price. So home price concerns information about homes sold in some New Jersey town in the year 2001, I think. So I want to understand what are the appropriate prices for the home, let's say, and let's explore it a little bit. So we'll use this multivariate sort of graphics package to sort of check what's going on. So let's just do a simple R code. Let's write it down. So let's create a panel, let's say, and then so let's say panel .lm. So .lm. And then I have to do, let's say I'll create it equal to, let's say, function of y. And then I just, I want, this is a command in lattice. So let's call it as, I think you do panel.xy plot. So panel.xy plot of, I want x comma y on one side. And the next thing I want is I want to put the lines for each of these guys. Panel dot is called ab line of y tilde x. Y tilde x. Let's do that. And then let's close the bracket. Very good. Then, so let's go down. Let's look at the head of home price. Let's say home price. Right, so it has this list of houses here and sale, full, how many bedrooms and rooms and neighborhood and so on. So let's just plot all of them separately. Let's say xy plot. So xy plot. Plot of sale tilde rooms. And let's say I pipe it to neighborhood is one panel. Neighborhood. And then I want the panel as in panel.lm. Yeah, we find above. And I take data to be home price right over here. This is like a lattice command. I just thought lattice to you guys so you can check lattice. So if you do this, let's just see what happens. So what happens is that if we do this, it's just, okay, let me combine, we start again, lattice, very nice. I'm gonna do this. So there are somehow there are too few points, right? So let's just add some more points, let's say. So we have to sort of there are some neighborhoods that are very, very few points. Very, very few points. And some have large, there's only 2 points here, and some have 3, 4. So let's combine them a little bit. Let's do a cut command. How do I do that? Let me just So cut command, and we do neighborhood equal to, let's just, I made a mistake here. Well, I have one more bracket. Let's do that. So I'm just combining them a little bit into 1, 2, 3. Let's just run that. And let me just check if I've done it correctly. Let's see how I do a table of neighborhood. So then let's see what comes. Yeah, I want 3 groups now. Each of them is fairly large number of people. That's good. So then I do the same thing. I go back and instead of neighborhood, I go copy this XY plot. And so now it's so nice. It's a 3-way plot. Give you 3-way plot. Yeah, I don't know why the ab lines are not coming, but it should give you why is it not coming. Let's just check. I do the ab line correctly. I did panel ab line. It's quite nice. So the ab line is not coming out. I'm not sure why. Oh yeah, so no wonder. I did LM of y to x. No wonder. Very good. So now it should be coming. Now I go back to the panel LM, and XY plot. There's two and then lines are some are too few lines, but too few points. The lines are still there. And I combine them to 3 things. I do a table, I check it correctly. I do this one. This is better. Very good. So this is one way of sort of giving sales versus rooms in each neighborhood. So you would have this multiple sort of sets instead. So now we can do the same thing. We can just say, so if you look at head of what's it called, home price. So you have so many bedrooms. Let's look at bedrooms and sales. Let's go home. So let's look at element of sales. I got the bedrooms and neighborhood. So let's do a simple regression. Let's do so this is what I want to try. So now so above plots sale versus number of rooms for each neighborhood. And this one, do that. You do summary, LM of sale, build up bedrooms, plus, and then I just add 2 neighborhoods. Let me cancel this. I don't want to save it here. Plus, let's say, let's do neighborhood as well, NBD that we did. So I'm doing multiple regression now. Let's put this. Let's see what it gives us. Put this out. It'll give you again what it's going to look like. So what is it saying? This is saying the sale is going to be 35 times bedrooms plus 115 times neighborhood. That means for every bedroom, you're going to pay about 35 whatever currency extra. And for a better neighborhood, you'll pay 115 rupees, let's say, extra. That's what it's saying. But what do you mean by negative intercept? Like, what that means if there are 0 bedrooms, somehow the house is worth sort of negative. The house is worth some number, negative number. So that's like a very small house in some sense. It looks kind of funny, but that's how we sort of run this. So let's do another one. Let's just do another calculation. So let's say, so that means let's say C. So let's just write down the thing. So 35.84 price per bedroom, unit price per bedroom, price per bedroom, and 115 per neighborhood. But each better neighborhood will cost you 115 more. Let's just do another regression here. Let's do neighborhood plus bedroom plus, let's say, what else do we have? Let's take another one. Let's look at the head of the data set again. Let's look at head of home price. Let's look at what full is. Let's look at what full. Let's put full as well. Plus full. So what does it give you? Let's see. So it gives you, okay, it gives you 67, okay, 31 again, 101, and so on and so forth. That means So if you have a full bath, I think the full is for the full bathroom. So if you have a full bathroom, you have a little bit more money, you put 28 units more. And it's kind of high, I guess. And it could be as high as. So now let's say we think, so that means it comes out to be, let's say full bathroom seems to cost 28 whatever units per price per bath price more. Let's say seems high. Seems high. I think for one bathroom you pay 28 more. It's a little bit more. So let's say we do a simple test. Let's just so this already gives you the error, right? The error is 18.9, right? It gives you the error. Let's do a simple test. So let's look at standard error of the estimate we know is 18.19. Let's take that. Let's do a simple test. And let's say we think the so this R is giving you for 0, right? R is giving you if the thing is 0. But we think, let's say the price correct price, let's say is 15. Let's say correct price, let's say is 10, is equal to 10, let's say. Suppose, for example. Then what are the t statistic? T statistic is going to be, the t statistic is going to be, what estimate we got was 28.51 minus the correct price we thought is 10 divided by standard error, which is 18.19. That's t, right? That's t. Right. Then let's see what t looks like. T is some number, it's 1.9. And we do the same t test, right? Let's do pt of t, comma, let's say, what's the degrees of freedom? Let's say how many things are there. Let's say n row of home price. So it's 29, so you have to remove 4 of them, so you get 25. Right? Degree of freedom is 25, and then 5, and then this is, sorry, let me save it. Cancel this thing. And then what was the lower tail equal to half? False, right? Lower tail equal to. Let's do that. Then we get the p-value is 0.84. It's quite high, so we sort of so that means we accept null hypothesis that the thing is like 10. So very good. So simple thing about multiple regression we've done from this data set of home price. You can do other prices as well. Let's see, let's try something. Let's say try 15. We can try something else. We can try it. Then we go here to 15. The t is 0.74 something, right? And then do the p-value that comes out to be again as 25. So I should do a mistake here. Let's just check df equal to 25. Include false. Let's check that. Yeah, no, sorry. I think by f I'm making a mistake. I think I'm sorry about that. Put false. So it's still quite high. It's okay. So more than 0.05. It's okay. It's also we don't accept the we accept the null hypothesis. We don't reject it. Very cool.